Hi everyone, we're going to work on tackling another fairly classic optimization problem. The idea in this type of problem is that you have a rectangle and you're either trying to make it fit underneath a curve or maybe inside of another shape like a triangle or a circle. So the dimensions of your rectangle are constrained by having to fit within that curve or shape. And we are trying to, within those constraints, find the biggest possible rectangle. So we're trying to find the maximum area. And if we want to maximize area, then one of our variables is picked for us. The dependent variable, the function, needs to be an area function. So I've got this picture, but let me go into it a little bit more with how this actually works. The rectangle is going to be set under this curve so that its top left-hand corner always touches the curve y equals square root of x. That point can move. What can't move is the right-hand side of the rectangle. The right-hand side of the rectangle has to be at x equals 9. So the right side won't move, the left side will. Just to try and give you a little bit of an idea of what that looks like, if we move the point a little bit to the left, our rectangle will get shorter but wider. Notice that the left-hand top corner is still sitting on the curve. If we move to the right, the rectangle will get taller but skinnier. Again, the top corner, the top left-hand corner always touches the curve. The right side always sits on x equals 9. So with that idea of that point being able to move around and get all these different rectangles, we're hoping to find the largest possible rectangle. So sometimes the tricky part of this is just picking your second variable. That second variable is supposed to help you talk about what you actually control in the problem. So really what we control is where the left-hand side of this rectangle is. And I think that A that was given in this picture is a nudge in the right direction. We don't have to use that variable, but I think the idea behind it is right. If we want to describe where the left-hand side of the rectangle is, we do that with an x coordinate. We want to say what is the x coordinate of the left hand side. And if you're more comfortable, you can use a letter besides x like a, but I think we're probably getting to the point where we're pretty comfortable just saying we're going to let x represent the x value of the left hand side, and I think we can sort through that. Okay, so into working on our formula, I've sort of picked out what I think a variable should be. And this is not the only option. You could let x represent the base of the rectangle. You could even probably let it represent the height of the rectangle. They might be a little trickier to sort out, but there usually are options in these problems. What I'm hoping to get is those things that I just mentioned, the length and the width of the rectangle, because that's what I'm trying to find, the area of the rectangle, which means I need the length and the width, and I need each of them to be in terms of what x is. Okay, so length, I'm going to call the base the length. And what I see there is that x is the distance from the y-axis to the left-hand side of the rectangle. And then the other thing that I know is the distance from the y-axis to the right-hand side of the rectangle is 9, which means what's left in between is 9 minus whatever my x is. So if I put the left-hand side at x equals 1, the base of the rectangle is 8. If I put the left-hand side at x equals 7, the base of the rectangle is 2. Okay, so first dimension is going to be 9 minus x. The other dimension is the height. It's basically our y. Height is y. Or we could look at it and say, I need the coordinates of this point. I need the y coordinate of that point. That would be the height of the rectangle as well, whichever way makes more sense in your head. And this part, once you've got it, is really easy, but at first it can kind of mess with people a little bit trying to figure this out. Remember that the whole thing that's restricting our choice on what is the base and the height of this rectangle is that it has to hit the curve y equals square root of x, and that right there just straight up told you what is y. It's the square root of whatever your x is. So if we put the left-hand corner at x equals a, the height of the rectangle will be square root of a. Again, we don't have to use a different variable. We can just say whatever our x is, the height is going to be the square root of that. So I called that width, I guess. We'll put a square root of x in there. And you could really leave the formula just like this. Since my goal is to take a derivative, I think I'll distribute through. So I get a 9 root x minus x root x. And again, you could leave it, but if we're taking square roots, I think rewriting those as power functions is a nice idea. So I'm going to say 9x to the 1/2. And then I'm going to do just a tiny bit of scratch work here. If I have x times x to the 1/2, that becomes x to the 3/2. Okay, so there's my formula. Often that's the hard part of these problems. Calculus can be tricky, but usually in the word problems, it's getting them set up that gives people the most trouble. From here, I have an area function in terms of only x. If I want to maximize, I'm going to take the derivative and find some critical values. So I'll drop the 1/2 down to the front, which will give me 9/2 as my coefficient. The new power will be 1/2 minus 1, or negative 1/2. I am also going to drop down the 3/2 in the second term, and the new power will be 3/2 minus 1, which is 1/2. So there's my derivative. I want to think about when is it undefined and when is it 0. This one actually is undefined. Note that that 9/2 x to the 1/2, that's the same as 9 over 2 root x. That's undefined if x is 0. It's actually undefined if x is less than or equal to 0. No negatives under square roots. But if you look back at your original area function, at any version of it, we weren't allowed to have negative numbers there either, so we don't really have to worry about the negatives, but the 0 is interesting because it was totally possible to have x equals 0 in the area function. It is now not possible to have that in the derivative function, which means I could be hitting a sharp corner or something interesting. So x equals 0 goes on my critical value list. The rest of them, or the other one, if there is another one, would come from setting this equal to 0. I'm going to go ahead and do that rewrite I said. I'm going to do 9 over 2 root x, not 2. And then I think I'll also move this 3/2 root x to the other side. You don't have to rewrite them as roots, but I think often it kind of triggers our process of how to solve a little better when we do. I'm going to clear the fractions next, so I'll multiply both sides by 2 root x, which means all that's left on the left-hand side is a 9. On the right-hand side, the 2's cancel, which is nice, and I'm left with 3, and then it's really just an x. Square root of x squared is just x. So I can divide by 3, and it looks like my other critical value is going to be at x equals 3. So I have critical values. I need to figure out which one is max and min. I think we can probably fairly quickly eliminate x equals 0, but remember you have to verify in general, if we're leaning towards x equals 3, that it really is a maximum. So we should go back and try and find the domain. And in this case, it's actually really definite. We don't have to think too hard or draw a lot of pictures, I hope. The smallest possible x value is x equals 0. It's a bad choice because if x equals 0, the top left-hand corner is at 0, 0, and really all we're getting is not even a rectangle anymore. It's all the way flattened out. It's just a line along the bottom of that section of the graph that we're looking at. So not a good choice, but it is the extreme, so 0. On the larger end, the biggest that we can make x would be x equals 9. And again, it's a very poor choice when x equals 9. Now the base of the rectangle is 0, and it just becomes a vertical line with a height of 3. So it's just a vertical line that ends up here at 9, 3. So 9 is the other extreme for this one. We already had 0 on our critical values list, so really our check to see if we found a maximum is going to be to plug 0 in, to plug 3 in, and to plug 9 in. And by plug in, I mean plug into the area function 0. Let's see, which version do I like? I'm going to go back to... Well, I like this version fine. Let's use it. When I plug in 0, I just get out 0. I get 9 times 0, which is 0. When I plug in 3, I get 9 minus 3, which is 6, times the square root of 3. When I plug in 9, I get 0 times 3, which is just 0 again. So this is definitely a maximum. That's positive. It's bigger than the values at the endpoints, so it's looking good. After this, make sure that you go back and reread the question. I was asked for the dimensions of the biggest possible rectangle. So if I was asked what is the maximum possible area, I would say 6 root 3. Since I was asked for dimensions, I need to give the base and the height. And actually, if you're paying attention, that's what we set up right here. 9 minus x was the base, and the square root of x was the height. So the base is 9 minus 3, 6, and the height is the square root of 9, or 3. So those are my dimensions. And again, for my purposes, as long as it's really clear to me what the shape should look like, I'm happy. In my open math, hopefully they'll make it really clear. I think they do make it really clear what exact information they're looking for. All right, thanks for watching.